To invite our first runner-up team, the Buffs, up to the stage to present their hack. Thank you.
Hi, thank you for having us here today. We're Team Buffs, and we're graduate students at University of Colorado Boulder. So this was our journey as we tried to implement segment routing in one day, within 6 hours, where we had to learn a lot of things. The idea was to automate traffic engineering in a dynamic way during real time. So once we had the hackathon problem set, we broke it down into achievable elements that we each took up, and then together we would finally integrate it into one working solution that we could run. The first step was to gather the topology information in the network in a dynamic fashion, and then it was to use the topology information to model a graph. We had to work on cSPF, because SPF alone would not achieve the requirements that were given to us. So we had to modify it for each of the problem statement, each of the different scenario, take into consideration the different constraints, whether it was disjoint path, whether it was the bandwidth subscription. So modify the algorithm to consider that, and then find the best path. And then the final two steps were to use once we had the best path, we had to dynamically configure the routes with the MPLS labels, and it was finally to push it to the network and validate and see if traffic is taking the path we meant it to take. So these were the steps. There's a visual representation of what we were trying to achieve. On the top left, we were gathering information, the topology information. We were working with Juniper devices, so we used Juniper's inbuilt library PyEZ. It makes remote procedure calls on all the boxes in the network, gets the information, topology information in JSON format. Then we pass through the JSON format to obtain a data structure, which is basically the LSA, along with some of the traffic engineering elements that the cSPF algorithm can use to make decisions. And the second step is in the top right, where we use the cSPF algorithm. We had 3 different scenarios, and we wrote 3 different functions wherein, based on the requirements, we run SPF, taking into consideration the constraints defined, and come up with paths that will work for each different scenario. Then we use then we use segment routing paths. We construct the routes based on the labels. We dynamically assign the labels to, and once we have the routes ready, we push it into the network. Using ExaBGP as an interface, it establishes a BGP session with the MX routers in our network, and then we push the BGP LU routes into our network. So regardless of what the forwarding table was before we did this, once we push these BGP LU routes, the route manipulation will take effect, and the paths taken will be the ones we wanted to take. So we're trying to do that in real time. So with topology discovery, as I mentioned, we use the PyEZ library, and this is what the data structure looks like. So for a given link, we have this information where it talks about the source in that link and the destination within that link itself. And it has traffic engineering metrics like cost, which in this case is 10, and 100 Mbps, which is the reservable bandwidth for that link. So we get this information, we parse it, and then that would be given to the cSPF functional block. So this was the topology information we discovered. While parsing it, we found 3 additional links than the topology that was given to us. But not to worry. The shortest path algorithm that we wrote works for any topology, so it was able to accommodate that as well. So we had 3 different scenarios. We'll go through all different scenarios and how we had to modify the SPF to accommodate for that scenario. The first scenario was straightforward, where we had to find the shortest path between MX3 to MX5. We just ran the SPF, and we were able to find the shortest path, which is as indicated, as highlighted in the diagram. In the second case, it was more challenging. We had to find as many disjoint paths as we can in the network. In this case, it was between MX1 and MX5. So the first step is still the same. You run SPF to find the shortest path between MX1 and MX5, and then you remove the links that were used, and you update the topology table, and then you run shortest path again, and you iterate over it to find disjoint paths. So once you remove the black path, which was the best path, you get suboptimal routes next, which are all disjoint, which are the blue paths and the red paths indicated in the diagram. So this is how you have to modify the SPF to accommodate for the second scenario that we were required to accomplish. Now, the third and final scenario, here the goal was to make sure that all of the link bandwidth is utilized. So here, again, we don't worry about the disjoint paths. The goal is that if user 1 is using an amount of bandwidth, so now so even though the topology information said the available bandwidth is 100 Mbps, if user 1 is already using 50 Mbps, you have to take into account what is currently available. So again, you need to subtract that from the pool of available bandwidth and then run the SPF. So that was the idea. So as multiple users use that, you keep giving them paths until all paths are possible. So that was the third scenario. And ExaBGP is an interface. So the output from the cSPF algorithm, it gives us the path. As you can see, it says MX3, MX2, MX5. That's still not the configuration. That's still not the route. We just have the path. So we have to use the code again to find the information. It has to go into MX2, find what is the IP between MX3 and MX2. And that's how the neighbor command looks like. You have an IP reference, you announce the route. So again, the code builds this during runtime dynamically without any intervention. So once the route is built, ExaBGP is the interface for us. It establishes a BGP session with the VMX router, and it announces this route, and it goes sits in the forwarding table. And once that's done, this is how the routes will look like. You can go into all the network. So these are the routes we saw on the VMX routers once the routes were pushed. As you can see a label reference. And for a given label, you see the exit interface and the destination for a particular destination IP. So if you're trying to reach from MX3 to MX5, it will take the labeled paths, and it'll take the path that we've manipulated it to take. So we are controlling the network using code. So these are the expected results. These were the labeled paths that we wanted it to take. Here are the screenshots proving that. So in summary, we learned a lot of things. We've been doing SDN since 2 months in our college, so this is a new thing for us. So it was a lot of things to learn about. There were many ways to parse the topology information as well. There was CLI, there was different tools that you could use. We went with the Juniper API because it's dynamic, it's reliable. So even if when you're parsing the data, you don't find any data, your code is not going to break. Your code is still going to work with whatever is available, and it parses that data. So that's why even though we didn't know the API, that was the right way to do it. So that we tried to learn that, figure it out, and then go about with that. And with the cSPF as well, for different scenarios, we had to write different functions to modify SPF so that that would fit the requirement that they expected us to achieve. So it was fun playing around with the SPF, which we knew, and tweak it a little bit. And with ExaBGP, we had a lot of issues installing it. The installation was not clean on using Python 3. So, and then with some help, we figured out that you didn't have to install the full features. You only needed a bunch of features to make these things work. So once we were able to work around that, we were able to solve the issue, use this as a tool, and kind of bring everything together. So it was fun. It was amazing to work with some of the best minds in the industry, be in the same room as them, interact with them, learn, and to build an end-to-end solution within a matter of 6.5 hours to kind of visualize what would happen and bring them all together was exciting. And it was an amazing experience. This is the first time we were working as a team as well. So to work together, to be in sync and build that rapport was a really good experience to have. And a lot of credit to all our team members. We worked at this together, and a lot of credit to Professor Jose Santos as well, who was here with us, and he was our guide through this as we worked on it. And special thanks to all the organizers. I think they did an amazing job putting together this event and have remote participants as well. That was great. And thanks to all of you for your attention. This is the contact details. If you have any questions, we're happy to answer. You can get in touch with us as well. Thank you.